Hello, am I audible? Yes, someone can reply. Okay, thank you. I will share a screen. I hope screen is visible to you all. Okay, fine. Now can I take marker here? Easy note. Okay. Uh, is the screen visible to you? Is the screen visible? I hope screen is visible to you. Chat box. Okay. Screen is visible to you. Someone can put in a message in a chat box. Screen is visible. Okay, okay. And I'm audible clearly. Fine. Now we have seen what is the graph in the last lecture. Let me show what is there in our syllabus. Then I will explain again. Okay. So that we can close this particular chapter. What we have in our syllabus? Let me take uh, this one. So we have. Okay. What we have in graph? So in I will we have started graph. Okay. Then later I will start with the tree. So graphs, basic terminologies and representation of graphs using adjacency matrix. What I have seen the basic terminologies. What is graph? Graph is a data structure where it can be represented by G equal to V comma E, where G is a graph and V comma E are what? V is a set of vertices and E is set of edges. Then we have seen what is adjacent. What do you mean by adjacent? If a vertex is a neighbor of other vertex, it is called adjacent. Then we have seen what are degrees, in degree and out degree. Okay, if there is a edge intersecting, okay, to the vertex, that is called a degree. If the direction is inside, it is called in degree. If it is the direction outside, it is called out degree. This is in directed graphs, that is they are also called as digraphs. Whereas in undirected graph, if there is a edge, that is called in degree. Okay, that is called a degree, not in and out, because it's a undirected graph. What else we have seen? We have seen what is cycle. Cycle is what? If I have a path, if I have a path from a vertex V and the other end is V, that is we visit all the different vertices and come back to the same vertex, that is called cycle. That is called cycle. A single and what is if I have a if I have a edge from same vertex to same vertex, that is called loop. that is called loop. Then if okay, I will draw those things and just visit again. Okay, maybe we will see the presentation and I will draw all of them, all the basic terminologies. Then we will come back to what is how to traverse, what is traversing, how to traverse all those things. Okay, so let us start. We have seen all these things, basic things. Okay, then we'll come back. So what have you seen? What are examples of why we use the graph? Because there are many practical problems like maps and whenever we have objects and we want to represent the link or a relation between the different objects, then graph is very useful. Like in computer networks, the route of different routers, if we take in physically like routes between different cities, different states, like maps, road maps, rail map, or airport mapping. Okay, in all these things it is very difficult to represent in computer, so graphs and trees are helpful in this in to represent these things. Basically graph, because we have to draw those physical things in terms of graphs first, then we can represent those things in computers. So generalization of the simple concept of a set of dots or vertex and linked edges is called graph. We have seen this graph is G equal to V, where it consists of set of vertices and set of edges. What is directed graph? If I have a direction marked on the edge, that is called directed graph. Okay, so order pair of vertices represented as U comma V, which is called as, is directed from vertex U to V. Undirected graph, unordered pair of vertices represented as U comma V. You can see this, it is in bracket, simple bracket U comma V, and there is a ordered pair U to V. Whereas in undirected graph, we have unordered pair of vertices represented as U comma V. This regards any sense of direction and treats both end vertices. So I can write it here as edge as U comma V or V comma E. That is in undirected graph. What is loop? If I have a edge from same vertex to the same vertex, that is called loop. What about multiple edges? If I have multiple edges, okay, this one U comma V. You can see this U1 and U2. There are different two edges between two vertices. So this is called these are called multiple edges, and the graph which is having multiple edges are called as multi graphs. Okay, what is simple graph? Simple graph consists of vertices, a non-empty set of vertices, and E, a set of unordered pair of distinct elements of B called edges. You can see this. There is okay. These are simple edges. There are not multiple edges here. So this is called simple graph. Simple undirected graph it is. Then okay, directed graph. If there is a direction written on every edge, marked on the edge, then that is called directed graph. What are now how to represent this graph? The graph G here, graph for this particular graph is represented as G of V comma E, where how many vertices we have? We have to write V equal to in set. V is a set of vertices, isn't it? So how you are going to write it? V equal to bracket, curly bracket, U comma V comma W. These are set of vertices. What about edges? Edges E equal to UV, VW and WU. UV, VW and W, set of vertices. So edges you have to write in bracket as it is direct, directed graph. So this is represented as such that. So direct multigraph, if there are multiple edges between vertices, that is called multigraph. Now you can see this. We have two edges and both the edges are in same direction. That's why it is multigraph. Suppose I have U1 from U to V and U2 from V to E in reverse direction. Then that is not called multigraph because the directions are of the edges are different. Okay, then that is not called multigraph. Okay. Now, what else we have seen? What is adjacent means what? U and V are adjacent. We call those both the vertices adjacent if there is a edge U comma V. Is an edge E is called incident with U and V. U and V are called endpoints. So if a particular edge incidents, that means connects two vertices, okay, then both the vertices are called adjacent to each other if it is undirected graph, okay. And if it is a directed graph, then we call incident to and incident from, okay. Now what is degree of vertex? A degree of vertex in undirected graph is number of edges connected to that particular vertex. So the degree of vertex, degree of V, the number of edges incident on a vertex. A loop contributes twice to the edge. Now where is we have seen loop? Okay, this is loop, isn't it? Here for W we have a loop. So if what is here? We have one edge going out and one is coming. No, this it's a directed graph. Let me take undirected graph. We have seen loop. No, this one. Okay, if this, suppose there is no direction, then we have edge connecting same vertex. That means 2 degrees if it is undirected. Okay, and if it is directed, then we have one out degree and one in degree of that particular vertex. So a degree of vertex, the number of edges incident on a vertex. A loop contributes what? Twice to the degree if it is undirected. If it is directed, then it will contribute to one in degree and one out degree. What are pendant vertex? Pendant vertex are one where we have only 1 degree if the degree is 1. So degree of V and W are 1. So they are called pendant vertex. What is the isolated vertex? Now here in this case, K is the isolated vertex where uh, when degree of particular vertex is 0, that means there are no edges incident on that particular vertex. They are called isolated vertex. What else we need in degree and out degree? For edge UV, U is adjacent to V or V is adjacent from U. Okay, U is the initial vertex and V is the terminal vertex. This is when if it is directed graph. Now U, we can take this example here. Okay, U is adjacent to V or V is adjacent from U. U is the initial vertex and V is terminal vertex. Sometimes we call V is we call head of the edge is V and tail of the this particular UV edge is U. In degree, number of edges for which U is terminal vertex. So for V, one edge terminating. So this is one. The in degree of V is 1. What about out degree? Out degree also 1 because one edge is going out of this. So that is the head for this. That is out degree is 1. Now we have seen all these things. Let me take some more examples. Simple graphs. Okay, special cases. Now, what is complete graph? Complete graph Kn is a simple graph that contains exactly one edge between each pair of distinct vertices. Now, represent these examples. We have K1, K2, K3, K4. All are simple graphs. Okay, simple graphs. What is complete graph? If I have a edge from a vertex to all other vertices, that is called complete graph. Now you can take this here. Now for K it is a single vertex, doesn't matter. For K2 we have a vertex. So we have vertex 1 to 2 we have a edge and 2 to means all the vertices can be connected here. You take this example vertices 3. So any of the vertex can connect to other vertices using a graph. So uh, we have independent edges to every other vertices. In this example, now this is a graph with 4 vertices and 6 edges. You can see that I have a edge from this particular vertex to all other vertices. So I can connect here, I can connect here, or I can connect here. It is same thing. So it's a complete graph. In a complete graph, every vertices will have edges to every vertices. So what is cycle? If I can visit, I can if I have a path. Path means what? Number of path is if I have a connectivity between two vertices, then that is represented by path. Okay. and if I can start with a particular vertex and visit all the vertices and I can come back to the same vertex, that is called cycle. We have seen this. Okay. Then what else we need here? Subgraphs. We have seen in one example what is subgraph. How to represent graphs. So graphs can be represented using adjacency matrix and adjacency list. Okay, let me take adjacency matrix. Uh, Representation adjacency matrix. Now there is an n into n matrix where number of vertices is equal to n. The adjacency matrix can be represented by n into n. Okay, n rows and n columns, and uh, 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 every element of adjacency matrix A of ij can be either 1 or 0. If there is a edge between I and j, we will represent it by 1 or by 0. So A equal to ij equal to what? 1 if Vi Vj is an edge of G, otherwise 0. For directed graph, 1 if Vi Vj is an edge of G or 0 otherwise. This makes it easier to find subgraphs and to reverse graphs if needed. So adjacency matrix is chosen on the ordering of vertices. Let me take matrix. Now we'll have some more terms. What is sparse matrix? The adjacency matrix simple graphs are symmetric. When there are relatively few edges in the graph, they are called the adjacency matrix is sparse matrix. And if there are multiple edges, many edges, then it is called dense matrix. Okay. Undirected. Now take this example. It's a undirected graph. Now we have three vertices. So the matrix will be 3 by 3. Now how we are going to write it? VUW, VUW. There are no loops. That is, there are no edges from same vertex to same vertex. That's why this diagonal element is 0. That means V to V, do we have edge? No, it is 0. U to U, it is 0. W to W, that is 0. But I have V to U and V to W edges. So I have to write V to U 1, V to W 1. So this is how we represent adjacency matrix. We have seen this in last example. Now for directed graph, you can see this UVW. U to V, do I have a path U to V? No. No, first we'll take V. V to V, do we have loop here? V to V? No, it is 0. V to U, I have a path, I will write it 1. V to U, V to W? No, it's a reverse direction this path edge. So we don't have V to W edge. So I will write it as 0 here. What about U? U to W, I have a path. U to V, no. So U to V, 0. U to U, no loop, 0. But U to W, I have a path. I will write it as 1. What about W? W to W, there is no path. So it is 0 here. But W to V, W to V, I have a edge. So I will write it as 1. What about W to U? There is no edge from W to U. So it is 0. So how this is represented? That is the graph. Now we can also represent graphs using adjacency matrix. So how it is done? Each node vertex, okay, has a list of which nodes vertex is adjacent to other. So we have to write a node like in a row, okay, single array, and we will use number of linked list, okay, for each node. So if you write a UVW, so U is connected to V and W. So adjacency list is what? V and W. So this can be represented pictorially like okay, maybe I will draw it later after this PPT. So let me take isomorphism. We don't need path. So what is path? Connectivity. Now, what is the connectivity? Basically, in a graph, reachability among vertices by traversing the edges. Traversing is visiting or going from or exploring or going from one vertex to other vertex using some edges. That is called connectivity or a path. Now, what are applications? In a city to city road network, if one city can be reached from another city, that is a path. Now problems if determining whether a message can be sent between two computers using intermediate links. So this can be represented by graph paths. Efficiently planning routes for data delivery in the internet. So all these things are examples of graph. and connectivity of graphs. What is path? A path is a sequence of edges that begins at a vertex of a graph and travels along edges of the graph, always connecting pairs of adjacent vertices. Now suppose I want to find a path from U to V. Do we have a path from U to V? Yes, we have to write all the edges. Now you can see this, I can go through U to 1, then 4, 5 and V. So I have a path here. Okay, I have a link from U to V. Now this is called a path. So representation example, suppose in a graph G, V, comma E, I want to find a path P represented from U to V is how you are going to represent it? You have to write these curly braces and all the edges through which you can reach V. So what is the first edge here? U1. So that is written here U1. Then 1, 4, 1, 4, 4, 5, 5V, 4, 5, 5V. So this is a path. So this whole thing is a path. You have to write all the edges between those vertices. And if I have a path U1, U4, U5 and V, then from V to U, if I have a path, if I can come back, that is called what? That is called cycle. Okay, that is called cycle. So definition for data graphs. Okay, a path of length n greater than 0 from U to V in G is a sequence of n edges E1, E2, E3 to En of G such that E1 equal to x0, x1, f function of E2 equal to x1, x2, fe, all these things. Okay. Now for simple graphs, sequence is 0, 1 and n, and if it is a cycle, then you come back and reach x0. In a directed multigraphs, leave it. What is circular cycle? If U and V length of path is greater than 0, that means for a vertex, if at least there is a one edge U to V, that is one edge, the edge coming up, the edge starting point is same and the last point is same, then that is cycle or circuit. So see this U equal to V, length of path 0. Okay, maybe I will draw a circle and explain you. Simple path does not contain an edge more than once. Okay, so we have to visit only once. We cannot come back. We cannot traverse with the same edge again. That is simple path. Undirected graph. An undirected graph is connected if there exists is a simple path between every pair of vertices. If there are every pair of vertices, if there is a path, so here it is a connected graph. So all the vertices can reach to other vertices here. Now, for example, representation example V, for V, V1, V2, V3, V4, V5, there exists a path between Vi, Vj if we have edge at least 1 to 5. Okay, what else we need? So these are directed graphs. Okay, so let me take representation of graph again on the board. Then we will see what is how to traverse. What is traversing? Traversing is visiting or checking the connectivity. Traversing is visiting from one node to other nodes. So let me take that first. Then we'll see. First, I will, we have seen how to represent graph in computers with using adjacency matrix and adjacent list. I will just show them, and I will take what is how to traverse with BFS and DFS. Then in the next lecture, we'll take a program for that. Okay. I think I have taken this one. We have taken how to represent this, but let me show you again. I will cover this one. Then we can move forward later. So how we can represent a graph? We can represent in two ways. One is adjacency matrix and other is adjacency list. So graph representation in computer. Graph representation in computer. Now there are three ways actually, but we will consider only two. These. With multi-list also it is possible to represent, but I am not taking that. We are in our syllabus. This is enough for us. We will represent using adjacency list and adjacency matrix. Suppose I have a graph. Suppose I have a graph 1 with 5 vertices. I think same example I had taken in the last lecture. Let me take the same one. 1, 2, 3, 4 and 5. If I have 5 vertices, and so this is a graph. Then you will write a program, okay, for this. Okay. Now, what is adjacency list? Adjacency list is a adjacency matrix, actually, first one. So this graph can be represented by adjacency matrix. First one, adjacency matrix. Adjacency matrix. Now here, what is adjacency matrix here? The adjacency matrix for this particular graph will be matrix M. I will take matrix A. Matrix adjacent matrix A will be n into n. N by n. What is n here? N is number of vertices. So here is equal to A of 5 comma 5 by 5 matrix. 5 rows and 5 columns. Okay, as vertices are 5, which is n, okay. Now this can be represented as how we have to write all the vertices is a matrix of n by n. So I will write the number of vertices 1, 2, 3, 4, 5, 1, 2, 3, 4 and 5. So I have a 5 by 5 matrix. Okay. Now let me take this matrix. Okay. Now you have to check whether there is a if there is a path, there is edge between edges. So do we have edge from 1 to 1? 1 to 1? No, there is no edge here. So it is 0. So what is loop here? For edge, say for this edge 4, if there is a edge here, this is called loop. This is called loop for a edge starting with the same vertex to same vertex. That is called loop. So we don't have loop in this particular graph. Let me clean this one. Okay. Okay. Then what about 1 to 2? 1 to 2 I have edge. So I will write 1. What about 1 to 3? 1 to 3 there is no path. There is no edge. 1 to 3, 1 and 3 are not connected. So I will write it as 0. What about 1, 4? There is edge between 1 to 4. I will write it as 1. Now next 1 to 5. No, there is no edge. 0. Then start with 2. 2 to 1, 2 to 4, 2 to 3. So 2 to 1 I have edge. 2 to 1 I have edge. 2 to 2 there is no loop. 0. 2 to 3 I have edge. 2 to 4 I have a edge, and 2 to 5 there is no edge. Then 3 to 2, 3 to 2 I have a edge, and 3 to 4, 3 to 5. Okay, so 3 to 2, 3 to 4 and 3 to 5 I have edge. What about 3 to 1? 3 to 1 no edge, 0. 3 to 3 there is no loop, 0. What about 4? 4 to 1, 4 to 2, 4 to 3, 4 to 5. So 4 to 1, 4 to 2, 4 to 3, 4 to 5 I have edge, there is no loop. 4 to 4 I will write it as 0. Okay, then 5 I have 1 and 2. So 5 to 3 and 5 to 4. 5 to 3 and 5 to 4 I have edges, whereas 5 to 1, 5 to 2, 5 to 1, 0, 5 to 2 is 0, and 5 to 5 there is no loop. So this is how it is represented. So this is adjacency matrix. Okay, and we have seen this in the last lecture also. Just explain this how this can be represented using adjacency matrix. Understood? Now we'll take the next one, which is adjacency list. Now let me take the adjacency list. So this is the first way, one way of representing the graph in computers. The other way is to have adjacency list. Second way is what? By using adjacency list. Adjacency list. Now what is list? These are singly linked lists. Okay. Now here we will have array of is single dimensional array of every node, and those many arrays will have each individual linked list. Now this can be represented with 5 array of 5 elements. So we'll have 1, 2, 3, 4, 5 arrays. 1, 2, 3, 4 and 5. So 1, 2, 3, 4 and array of 5 element. Then each vertex will have individual linked list. Now check, do we have 1 to 2, 1 to 4 link? Yes. Then what you should do? You should draw a linked list. I have 1 to 1 to 2. 1 to 2 linked list, then this will connect to the next node if I have other nodes here. So 1 to 2, 1 to 4. What about 2? 2 to 1, 2 to 3. So 2 to 1, 2 to 1. Okay. This is, I can write it here, 1, 2, 3, 4 and 5. Okay. If you want, you can write it here. Otherwise, you can remove those things. That is okay. So 2 to 1, I have a link. 2 to 3, I have a link. 3. Then 2 to 4. 2 to 4, I have a link. What about 3? 3 to 2. 3 to 2, I have a link. Then 3 to 4, 3 to 5. So 3 to 4, I have a link. Also, I have 3 to 5 a link. Okay. What about 4? 4 to 1, 4 to 2, 4 to 3, 4 to 5. So I have a link with 4 with all other, vertices. So 4 to 1, 4 to 2, 4 to 3, 4 to 5. Okay, what about 5? 5, I have only 2 links, 1 and 2. So 5 to 3 and 5 to 4. So 5 to 3 and 5 to 4. And the last node in the adjacency matrix, this should be put as null. So that is the end here. That is end, null. Understood? So this is how to represent a graph using adjacency list. Now, what are the advantages of using this? If the matrix is sparse, if matrix is sparse means there are less connections, less edges in the graph, then you should use adjacency list. So adjacency list is used when it is a sparse matrix, okay, or sparse, or the graph is sparsed, okay, not denser graph. Sparse graph you can use adjacency list, and for denser graph, okay, denser graph is used in adjacency matrix. Okay, so this is for so if I can use adjacency matrix if there are many edges, okay, many edges in the graph, then we should use adjacency matrix. If the edges are less, I can use adjacency list. Okay. Now let us what is traversing here? Traversing, graph traversing is if I want to see whether there is a path between say 1 to 5. If I want to see there is a path between 1 to 5, now how many paths will be there? I can visit 1 2, then I can go to 3, I can go to 4, and I can reach 5. In that case, what I will write? I will write 1 comma 2, one edge, then 2 comma 3 second edge, then 3 comma 5. So this is what this is a path. Now as it is undirected, I should use curly braces here. I should use curly braces. Okay. So this is a path. So what is the path value here? Path value are 3 edges, 1 2 3. So that is the value, or path, the cost of that is this particular path is 3 edges. Now I have not written any weights here. If you write every edge, if you write some value like 4 1 6 2 3, okay, if this is the distance, then that is called as what are they called? They called weights, and this particular graph is called as weighted graph. Let me take this one example. So what is weighted graph? If I write 1 2 3 4 and 5, and on every edge if I write some values, okay, if I write some values, say 4 6 3 2 10 7 4. So what are these? This is called weighted graph. And weighted undirected graph it is, because there is no direction here, but every edge has some value. Every edge has some value. Okay. So this is called weighted graph. If you write a weights on the graph edges, it is called weighted graph. Okay. Now we'll see what is BFS and AFS. So what is BFS and AFS? BFS is called breadth first search, and DFS is depth first search. So two traversal graph traversing. Let me take this. So what are different traversals? Graph traversals. So graph traversals techniques or methods. Traversals or traversing. Okay, how to traverse or visit a graph from one vertex to other vertex. So what is the first one? First one is BFS, breadth first search. Okay, breadth means we'll visit breadth first search. That is, we will go level by level. It's also called level searching. Okay, level searching. Second is DFS, depth first search. Depth first search. That means we will keep on searching all the neighbors from one level to other level in the depth. Then we will come back and we will visit our neighbors. Depth first search. Okay, this is called depth first search. I will take one graph, sample graph, and we will implement the same thing. Suppose I have a graph, say 0, okay, 1, 0, 1, 0, 1, 2, 3. Okay, we have edges here. It's an undirected graph. 0 1 2 3 5. Okay, let me take two more, 4 5 and 6. 4 5 6. Okay. Now this is a graph. If this is a graph, what is traversing? Traversing is checking whether connecting visiting from from a given vertex to all the vertices in the graph. So you can take any of the node as a starting point. Okay, if it is given if it is a tree, if it is I think a tree is started no in your DMS subject. If it is a tree, always root is the starting point. But in graph, there is not such that there is no root here. So you can take any of the vertex and start visiting all other vertices. Start traversing all other vertices. So we will use you can use anything here. Let me take what is some of the points in BFS. So if it is breadth first search, what we'll do? Choose a starting vertex. Okay. So the starting vertex. Suppose if I choose a starting vertex, say this one. Which one? 0. If I choose a starting vertex 0, the distance is what? It's a 0 it is because it's a starting vertex. Then vertices are visited in order of increasing distance from the starting vertex. Then that is we will visit we'll see 1 and 3 as it is BFS breadth first search. We'll visit all these things. Then from once if they are visited, suppose this is visited, I will mark it as visited. Then I'll visit 1 and I'll write 1 and 3. I'll choose one of the vertex 1 and 3 and I'll visit 1. Okay, then 3. We'll examine all the edges leading from vertex at the distance. Then examine all edges from vertex at distance d plus 1 to distance. Let me take a proper example here. To represent this in BFS, what we use? We use BFS, we use Q. Now, suppose this is the same graph. I want to traverse from a given vertex. So let me take. We'll clean this one, and I will draw the graph, and will take the BFS. Okay. So BFS will be BFS for this particular graph will be what? BFS. BFS is what? Breadth first search. Breadth first search. Okay. Now let me draw this. We have only we have next lecture here. So 0, 1, 2, 3. Okay. And we'll have some more 4, 5, and 6. Okay. Okay. Now, for BFS, we use stack. BFS, we use stacks data structure to traverse. Suppose the starting point, it is 0, no? Starting point is say 0. I want to visit from 0. What I will do? See, suppose this is the starting point. Then, in a what is this? It's BFS. So if it's a BFS, if the starting point is 0, we will use Q, not stack here. This is for BFS. For BFS, we use Q. Okay. Initially Q is empty. Initially Q is empty. What I will do? The starting node is 0. I'll push into Q. We will not call push. We call NQ. Okay. NQ into Q because push and pop is in stack. So what you do? You take the first vertex which you want to from where you want to start. You push into NQ into Q, insert into Q, and print. You also print the result. So result is what here? Result which you will print on the output. You print what? 0. You print 0. That is the first point. Then what you should do? You should mark it as you should mark it as it is printed. It's visited. You write the logic for this. You mark it as visited. Then check what are the neighbors of that particular vertex. So we have 1 and 2. If 1 and 2 are neighbors, you push those 1 and 2 here onto Q. 1 and 2. You push 1 and 2. Then go to vertex V. Take vertex 1. You print that 1. Print that 1 and check what are the neighbors here. Okay. So 1 is taken. What are neighbors of 1? Neighbors of 1 are 3 and 5 and 6. So you push those things. 3, 5 and 6. 3, 5, 6. Now you should insert vertices which are neighbor to that particular vertex and they are not inserted or not seen. Okay. So here 0, 1. So 3, 5, 6 are inserted here and 1 is taken out. Now next is, what is the next in the queue? We have 2. Now print 2 here, print 2, okay, and check all its neighbors. So which are the neighbors here? Neighbor to 2 are 3, 4 and 1. 3, 4, 1, but 1 is already inserted, so you'll not insert into queue. What about 3? 3 is also inserted. So what is left here? Only 4. So I will insert 4. I will insert 4. So this is taken. Now next take 3. So 2 is over. So take 3 from the queue, print it on the output, and now check what are its neighbors. Its neighbors are 2, 1. They are already taken. They are already seen. So we don't have to visit again, insert into queue. 1 is over, 2 is over. What about 5? 5 is also over. 1 is over, 5. All these they are over. Now there are no other vertices to insert into queue. So you don't have to do anything. Just remove this one. So what is the next element in the vertex in the queue? Which is 5. So print 5 here. Print 5. Okay, and check its neighbors. Its neighbor are 1 and 3. They are already seen. They are already inserted into queue and they have taken a traversal. So you don't have to do anything. Now come back to 6. So this is over. Come back to 6. Now 6. What are the neighbors here? 4 and 1. 4 and 1 both are already visited. So you don't have to do anything. So just print 6. Now what is left? The last one, which is 4 here. Check all its neighbors again. Its neighbors are only 2 and 6. Already they are over. 2 and 6 are over. We have visited and inserted into queue. We have to use some flags. We'll see later how to implement this in program. So once this is done, we'll print it in 4. So how we are traversing? You are starting with 0, 0. Then we are visiting 0, 1, 0, 2. Okay, 0, 1, 0, 2. After that, 3. After visiting 3. Then what? Then 5. Then if you write this, it will be like 0, 0, 2, 2, 1. Then after 0, 1, 2, after 2, 3, say 3. Then 5, 5, 6 and 4. Now this will be a sparse matrix. If I have to write here 1 and 2, then it will be a sparse tree. What is it called? Spanning tree. It is called spanning tree. No, this one is called spanning tree. There won't be any cycles or loops in this particular tree once we represent. So this is how to represent. This is how we can traverse in using breadth first search. That is, we start with a neighbor. We start with the vertex, starting vertex, visit all its neighbors. Then we take one of them, one of the vertex, visit all its neighbors, and we keep on doing this till we visit all the vertices in the graph. Now we can see this. This is a one of the BFS, breadth first search. There can be many BFS here. If you start with the same vertex, take this. Now I written here 0, 1 to first here. But if I write it 0 and 2 1, it is okay because both are neighbors. Both are neighbors. In that case, 2 and 1 come here. 2 and 1 will come here, and 2's neighbor. 2's neighbors are what? 3 and 4. So this 4 will come here next. 3 and 4. So this will be there will be many traversals in this particular thing. So it's 12:30. We'll stop it here. In the next lecture, I will just revise again what is DFS, and write both the program. Understood BFS? How the breadth first search is done? In a breadth first search traversal, we use queues. Okay, and we visit to start with a particular vertex. We visit all its neighbors. Then one of the vertex is taken. One of the neighbor vertex is taken. We visit all its neighbors. We keep on doing this till we visit all the vertices in a graph. So this is BFS. In DFS, we start, that is the depth first search. We visit starting vertex to the neighbor vertex. Then we take one of the neighbor vertex and we keep on visiting all the uh, vertices which are depth in level. That is, we go to this next vertex, not neighbor. Take one of the neighbor, but we keep on visiting to the depth. And we come back again, we visit all the vertices. We'll see in the next lecture. I will revise this again BFS, and in just 5 minutes I will revise what is the BFS, then we'll take DFS, then we'll write programs. Any questions? If you have any questions, you can ask. Okay, shall we end it here? Then we'll end it here. We'll start maybe. I will check. Do you have any lectures in the afternoon? It's okay. Maybe later I will see in the WhatsApp group. We'll see. Okay. We shall stop it here. Stop sharing and end the meeting.